Now let's just move on further towards the next theorem, which says that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Now we have to prove that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Means it is actually the converse of the previous theorem, in which we have proved that the diagonals bisect each other in a parallelogram, and now we are proving the converse of this particular theorem. So let us suppose if I'm just starting with the figure. As you can see over here, I have taken this particular quadrilateral in which the diagonals are bisecting in such a way that OA is equal to OC and OB is equal to OD. Now I have to prove that ABCD is nothing but a parallelogram. So let us suppose if I'm just starting with the given conditions. So what are given over here? Given is nothing but a quadrilateral. A quadrilateral we have, which is A, B, C, D, such that its diagonals bisect each other. Its diagonals bisect each other. That is, OA is equal to OC and OB is equal to OD. This is actually the given condition to us. Now what we have to prove over here, we have to prove that A, B, C, D is a parallelogram. So if we'll just prove this thing that the both pairs of the opposite sides are actually parallel to each other, so it is quite enough for us to prove that ABCD is a parallelogram. So let's just start the proof of this particular theorem. So the proof of this theorem would be like, in the triangle OAD and the triangle OC, we have OC and B, OAD and OCB. What can we say about these two triangles? First of all, as you can see over here, that OD is equal to OB is given to us, OA is equal to OC. These are the given conditions to us. Furthermore, we can say that the angle AOD is nothing but the angle COB, because it is forming a vertically opposite angle. So it implies that they are actually is equal to each other. So it means this angle is nothing but is equal to this angle. So hence at the end, what we can say from these three given conditions, that by SAS, side angle side criteria, we can say that the triangle OAD is congruent to the triangle OCB by SAS congruence rule. We can say about this fact. And since if these two triangles are congruent to each other, then we can say that the angle OAD is equal to the angle OCB. We can say this thing, that this particular angle is equal to this angle. We can say this thing. Okay, so this angle is equal to this angle. We can say this thing by CPCT. By CPCT, we can say this thing. Now, furthermore, in a similar manner, if I'm just taking the other two triangles. So let us suppose if I'm just starting with similarly, in triangle OAB and triangle OCD. So let us suppose if I'm just taking the two triangle, which is OAB, now I'm taking this triangle, and now I'm taking this triangle, that is OCD. We can further prove that the two triangles are congruent. It implies in triangle OAB and OCD, we can prove that the triangle OAB is congruent to the triangle OCD, and if they are congruent, then furthermore we can prove this thing, that the angle, which is nothing but the angle OAB, should be equal to the angle OCD again by CPCT. We can say this thing, that this angle, let us suppose if I'm just taking this angle, is nothing but is equal to this angle. I can prove this thing again. So again further, let us suppose if I am just putting it under this box, let us suppose from this condition and from this condition, what can we say? So let us suppose if I'm just taking it as 1, I'm just considering it as nothing but 2. So we can say from one, we know that the angle OAD is nothing but is equal to the angle OCB, and they are forming a pair of the alternate interior angles which always are made between the two parallel lines with the transversal BD. So since from OAD is equal to OCB, not the transversal BD. You can see I'm just talking about this angle and this angle, since they are forming in between the transversal AC. So what can we say? We say that if this is equal to this, if this angle is equal to this angle, and AC being a transversal and AC being a transversal, then angle OAD is equal to angle OCB are actually the alternate interior angles. And if they are the alternate interior angles, then they are formed in between the two parallels only. So hence it implies that we can write that AC is actually being a transversal between the two parallels, which is nothing but AD and BC. It implies AD is parallel to BC. AD is nothing but parallel to BC. And again, from the equation number 2, we can say that if angle OAB is nothing but angle OCD, they are forming a pair of the alternate interior angles. They are forming a pair of alternate interior angles that are formed between the two parallel line. Alternate interior angles that are formed between two parallels, and a transversal So for this, the transversal is actually nothing but again the transversal that we are taking over here is again nothing but this AC. So and the transversal AC. So we can say that it implies that if AC is nothing but a transversal again, so AB is nothing but parallel to DC. AB is nothing but parallel to DC or CD, we can say. So hence it implies that we are getting AD as parallel to BC, we are getting AD parallel to BC, we are getting AB parallel to DC, we are getting this as parallel to this, and we are getting this as parallel to this. It implies that both pairs of a quadrilateral are parallel. So it implies ABCD is a parallelogram. So ABCD is nothing but a parallelogram because both the pairs of the quadrilateral are parallel to each other. So this is nothing but the proof of this particular theorem.